the things that I'm going to speak about here are largely only present in Dyalog version 20 and onwards, which means you can't actually play with them quite yet unless you ask Dyalog for an early access to version 20. So version 20 does exist. Everything here does work. I have tried it, but you can't just do it in any old version of Dyalog. So first, a recap of what array notation is. It's something that I have spoken about on multiple occasions, written about it as well. And as a quick summary, square brackets, which are normally used for indexing and access, if they have multiple lines in them, and the lines don't have to be actual physical lines, they could be just separated with diamonds as well, then it is instead array notation. So that nothing is ambiguous here. And that means a higher rank array, meaning rank 2 or higher. So even here, where the constituent cells are scalars, we'll treat them as vectors so that we get a matrix. So this would be a 2-row, 1-column matrix of the letters A and B. And anything you would put in on these lines would become otherwise major cells of an array. And if they're just vectors, then you get a matrix. If we use round parentheses with the same rules, then we just get a vector. So here's nothing special going on. This would be exactly the same thing as writing a strand with these two character vectors. You could also write it on a single line with diamonds in between. And this allows you to write larger character constants, we could call them. Something that's quite common in vectors. So vectors over multiple lines so that it actually looks the way you would eventually print those. Slightly more exotic is a literal notation for a namespace. So this is not a script like you have in Dyalog, which begins with colon namespace. Rather, this is more like a declaration that we have a namespace, and you can differentiate this from the notation for a vector by having these unenclosed colons. So whereas the vector notation, the array notation for a vector, just consists of APL values, it could be expressions that give values, then the notation for a namespace consists of name value pairs with a colon in between. And you cannot mix and match. So you could not have a name value pair and then just a loose value. That would be a syntax error. As I mentioned, you don't actually have to use multiple lines. You can use diamonds as well. The only important thing is that these parentheses or square brackets must have at least one line break or diamond to disambiguate from existing meanings of the symbols. And then it sort of comes out as an edge case that just open paren, close paren, like this. It doesn't need a new line or a diamond because this doesn't have any current meaning. This is just a new empty namespace, something we very often want to do. And this is a very convenient notation for it. So this complements a quote, which is an empty vector, and we have a tilde, which is an empty numeric vector, and then we have open paren, close paren, which is an empty namespace. Okay, so I'm going to largely focus on a fairly trivial utility function, but something that comes out every once in a while. And that is we're going to generate a range. We're going to start from a starting number, and we're going to increase, to keep things simple, until the ending number. And then we're going to have a step size as well. So this should be very clear. This is just traditional code. And the actual formula we're using here, it doesn't really matter. That's not what I'm going to focus on. But just for completeness, we start with the starting number, and then we compute how far it is from the ending number, or from the beginning number to the ending number. Divide that by the step size. That gives us how many steps we need. Use iota to generate that many indices. Multiply them by the step size. So this gives us a progression vector. and then we just need to increment that with the starting number so that it starts off with the right next value after the starting number. So this is so far traditional APL. And we can try it. So here we're going to generate the numbers from 10 to 18 with a step size of 2, 10, 12, 14, 16, 18. So far, everything as it has always been, or at least has been for a long time. I mean, we are using some relatively modern features here, that we have a name list as argument, or as right argument to a function, and I'm also using the commute or swap operator, but it has been around even in APL Plus for a long time. But to be a utility function, we want it to have as much utility as possible. And very often, we don't want to specify all the parameters. So let's say that if we specify all three numbers, then it's indeed the from, the step, and the to. But we also want to be able to leave out the step. It's pretty obvious. If you're leaving out the step and just do from and to, then we should keep a step size of 1. So here, to keep the code nice and short, I'm using a fork, a train from Dyalog APL. And the way you read this is that you have the three parts inside, the take, the one, and the drop. And the two functions, take and drop, are applied to the outer arguments, the one and the args. So we do one take of the args, concatenated with a 1, concatenated with a 1 drop of the args. So effectively, it inserts a 1 in the middle. But that's not what I want to focus on. Let's continue. If you only give one element, then, and it could be a scalar as well, that the tally instead of shape takes care of normalizing that. Then we just prepend 0 as a starting point and 1 as the step size, and then we have the ending point preserved. Now, this is a lot of verbose code, so you could maybe come up with some very clever algorithm that could combine all of this, but that's not the important part. I'm just compressing this for you so that it doesn't take up so much space. Okay, so here we have an example where we're only specifying the from and the to, but we're not specifying the step. There's a problem though. This is a very simple function, but in general, when you make a utility function, often you have additional parameters, additional options you want to add, and it can be hard to remember the order of the arguments. And you also need special fill values that you can put in those slots that are in the middle when they're position based, so that you don't change anything, you just use the default value. And that can be hard to use, it can be hard to remember what the order is. Here we said from, step, and to is the ordering, and then you can leave out the middle one, and then you can leave out the first one. But what if I do want the default starting point, but I do want a special custom step size? So I want to start from 0, that's the default, and then I want a step size of 2, for example. And also, do we really remember what the ordering is? Is it from step 2, or is it from to step, or is it step from to? And that's just for this very simple utility function. If you do anything more complicated, then for sure you're going to have issues with this kind of thing. And this is where the fun really begins. So let's say that we change the architecture completely. Instead of supplying individual numbers as argument, we're going to supply a namespace. And that namespace is just a single argument, a single scalar, but it contains values with names that we have agreed on in advance. So you can just create this namespace and have populate it with the values that you want with those names, and it doesn't matter which order you're populating because it goes by name, not by position. But we need to extract our values from there. So we can use quad_ns for this. And quad_ns, until before version 20 of Dyalog, could only take a character left argument, which was the name of a namespace where we wanted to merge values in. But from version 20, it can also take a reference, And so since we don't want to deal with any special namespace here, we just want the namespace we're in right now, then we can give it quad this, which is a reference to the current namespace. So this merges, it takes all the variables that are inside the params namespace that we're feeding to range and merge them into the current namespace. And hopefully there will only ever be the names from and step and to, and that are the ones that we have localized as well, so they don't leak out of this function. Of course, if the user specifies any other names, they will also get merged into this namespace and they will leak out. And then we need to deal with having the default. So we can do that by just setting those in advance. So if we start off by setting from and step to the default values, then when we merge from the parameter namespace given to the function, that will overwrite the previously given values of 0 and 1 for from and step. So effectively, we have specified defaults for from and step, but not for to. So if the user doesn't specify a variable inside this parameter namespace with the name to, then we'll get a value error, which we could then, of course, trap this and give an error message and so on. But let's not worry about that here. That's trivial. Okay, so let's see how we use this. We can create a new namespace, and then we can populate this namespace with the parameters that we want. And we call the range function on this namespace, and we get our result. But remember that from version 20 of Dyalog, we now have the array notation available. So instead of creating with the system function quadns this namespace and then populating it, we can directly declare this namespace. So you see how nice the syntax is, that this p namespace is just from being 10 and to being 18. And that also means we can call range directly on the namespace. We don't have to create it first, the way we had to do with quadns, because we are directly both creating it and populating it. And this gives for a interesting call syntax. There's nothing going on special with regards to APL syntax here. The parentheses here just create a namespace, and we're calling range on this namespace. However, you can sort of forget that. You can sort of think of this being a call syntax that's similar to many programming languages out there, non-APL programming languages, where you call a function using parentheses to the immediate right of the function name, and then you state parameters inside those parentheses. Those languages tend to separate with a comma, but in the APL, the separator is, of course, diamond. So you can just think of this as a call with named arguments rather than call with positional arguments syntax. And we can exploit another extension in quadns. So until now, quadns has only been able to take a single namespace as its right argument. And it will then take that namespace and merge into whatever's on its left. But from version 20, we can use multiple namespaces on the right, and it will merge them in order from left to right. So what happens here is we have quad this, that's the current namespace, and we have two namespaces on the right. The first one is a literal notation namespace, and the second one is the one that's named params. So first we merge in the from being 0 and the step being 1. That sets from to 0 and step to 1 in the current namespace, and they're local. And then we merge in params to overwrite if those values have been set in params. If they are not set, they will not overwrite. And again, 2 has to be set. We could, of course, also in the defaults namespace, the literal one, have a 2 value so that we have a default value for 2, but that seems a bit excessive and not really useful. And we can then avoid the localization by generating a new namespace. So quadns without a left argument generates a new namespace, and then we can just capture this namespace and dot into it, and Dyalog allows a whole expression in parentheses after the dot. So this whole expression with the from, the step, and the to is now happening inside the namespace. this creates a new namespace, merges in the literal namespace with the from the step, and then merges in the params. But there's really no reason to create a new namespace here because we're already creating a namespace in the defaults namespace. So we can swap the order, and now we start off with a new defaults namespace that gets created every time the function is run, and we merge the given parameters into the defaults namespace. So it's not a defaults namespace anymore, it's just a namespace that we can use. Now you can notice that we're only using this ns variable once. I didn't even bother to localize it because the next step is going to be to inline everything. Of course, this makes for a very long, sort of unreadable line where we placed the result of quad ns inside parentheses to the left of the dot, because quad ns, when it's called with a reference left argument, and in this case it's a literal namespace we have there, it returns the same reference. So we can continue our computation directly. This is a bit unwieldy, but remember that we are allowed to shape our code, so to say, whichever way we want, as long as there is at least one diamond or new line inside the namespace. So we can remodel our code such that the defaults namespace is spread out over multiple lines. And that's really the important part here. You can see how the code sort of forms documentation, internal documentation for the function itself. And it's really quite readable, if you ask me. A benefit of having an array or a namespace here spread over multiple lines as opposed to the traditional single line is that you can put comments inside a literal. So here it's a literal namespace and we've got comments in it, but we could, if it was a vector, we could also put comments inside it, or comments inside a matrix, anywhere. We are also allowed to have blank lines or comment lines that don't have any content at all. So you have a lot of freedom on how to design your code visually. We can also use this in a defen, and it really comes out very clean there. There's a very little noise and a very high ratio of things that actually do something to the visual noise. So what we've seen some examples of is really a type of programmatic assignment. Right? We are creating new variables inside namespaces, variables that were not there before, even though we were not using the assignment arrow. And these two forms, with a character left argument to quad ns, or just no left argument, which creates a new namespace, and you can mix and match the right arguments as well. Those are things that have been in Dyalog APL for a long time. If you give it a list of names on the right, then it will take those names and create those names inside the namespace on the left. Or if there's no left argument, create a new namespace that has those variables. It will pick up the values for those new variables from the surrounding scope, from wherever we are right now. And if you give it a namespace, then it will clone. It will take everything from inside namespace and stick into whatever's on the left. If there's nothing on the left, then it will create a new namespace with the same contents. So it's effectively a clone of the old namespace. They're not the same reference. And extensions then in version 20 include that we allow a reference left argument. It's very useful. Not always you have a name for the namespace you want to deal with. And it's not always that formatting a reference gives a name that you can use either. It could give something with a square bracket that just says namespace in it. And as I mentioned, we allow multiple namespaces on the right, and they will get merged in turn. And you can use this to create a hierarchy. So you could have like some absolute defaults that we fall back to if nothing else has been provided, followed by some user defaults. These are the things that I usually want when I use this application, followed by some parameters given at this particular invocation of my utility function. Or you could add more levels. You could have a machine default followed by a user default followed by whatever I specify here. So this makes it very easy. There's also a nice symmetry in that you can actually make a quad ns reduction, and it will give the same result if you prepend an empty namespace. So this creates a new namespace, and then if you wrote quad ns and then empty namespace and then followed by some other namespaces and then reduced over that, then it will give a similar result. However, it's not always we are dealing with namespaces, juggling those around. Sometimes you just want to set a value. It could be inside a namespace, but we're not necessarily copying values from one namespace to another. And here we have an entirely new system function called VSet, or value set. And on the right, this is the syntax we have. We have a namespace on the left. If you don't give a namespace, it will default to this namespace that we're in right now. And then you give it name value pairs. So these are 2-element vectors of a name and the value. And the name has to be a character vector, and then the value could be any array. And it's replacing some code that I think a lot of people writing larger systems and applications have found themselves forced to use, which is to create APL expressions that include an assignment and then execute that, possibly inside a namespace. And that's a really just dirty way to do things. It's both very slow and it's very risky, because if the name contains some code, then that code will be executed without any verification. So if you have some kind of system where you're asking the user what name do you want to store this under, and then you store a variable with that name, and the user writes the name as, for example, quad off or something like that, then or quad off diamond name, then the system will just shut down when you try to make this assignment. Quad VSet, in contrast, is entirely safe. If you try to assign to a name that is not a valid APL name, it will just refuse. So you cannot hurt the system like this. Of course, if you're exposing this directly to the user, you might want to check that there are no dots or hashes in the name, so that you don't overwrite things other places than right here. Sometimes, instead of name value pairs, you've got a list of names. So traditionally in APL, lists of names are matrices. So we indicated that here. If you got a list of names, you can have a list of values, and then you can set that. It works just the same. And quad VSet knows the difference because the first element is a matrix. The traditional way of doing this is again with an execute, and it causes problems often when you only have one name instead of multiple names. There's lots of edge cases that are not even covered by the expressions you see on the left. And then if you want to create a new namespace with some particular values in it, then you can just use the notation for that. Just open paren, close paren on the left, you got a new namespace, and then you set values inside this new namespace. So this is how we can do it programmatically. Complementing this, even though it's not in the talk of the in the talk title, we can also get names, get values of names, something you traditionally use execute for. Again, dangerous. If the name is something that's not a valid name or some code, then that will get executed, and it's again very slow. Looking up a name in the interpreter's internal symbol table is an extremely fast operation, one of the fastest you can do. However, execute sort of has to spin up an entire execution environment, and that's very slow. So we have quad VGET to get the value of name, one name of multiple names. And again, it can take a namespace as left argument. If you leave out the namespace argument, it will just do it from the current namespace. Sometimes you want all the names from a certain namespace, and you have to sort of jump through hoops to do that currently. So this gives us name value pairs. We get a list of names, and then for each name we expand it to be the name and its value. So this gives us name value pairs. And we can just do this directly with quad VGET. So -2 it sort of indicates that if we want the nested result, we want the name value pairs. And you can use all the valid name classes, here you can give it a vector of name classes. Normally you want the 2s, which are the variables, but you could also use 9 to get namespaces and 1 for labels. You cannot retrieve the value of a function or an operator. Again, to keep things safe. And if you just want all the names as a list and you want all the values as a list, then traditionally you have to write some rather long and complicated incantation for that. But with quad VGET, you just give it a 2 instead of a negative 2, and you get names separately as a matrix and values separately as a vector. And you'll notice then that the results of quad VGET match the arguments of quad VSet. So you can retrieve names and values and manipulate them and then feed the result back to quad VSet, so that you can do transformations between values in namespaces or names in namespaces. This allows you, for example, to take one namespace that has lots of lowercase names, and then you can uppercase the names themselves and then set all of that into a different namespace, and you effectively uppercased a namespace. You uppercased all the names inside the namespace. And many other things you could do, insert prefixes and suffixes and so on. Okay, so let's see how we can use this in practice for something that's actually useful. So here is a CSV file, say, and we're going to read its content in just as text, and just to have a look at what it looks like. So the first few characters. These are just some random names that I generated. Don't worry about it. Okay, so we're going to, instead of reading a CSV file in as a matrix, which is a traditional way of looking at it, we want a namespace that we can work with, because we can sort of see that it's a columnar database. We have first and last, and each value here is a vector of values. This makes querying much easier. We'll see that in a moment. So we're going to use quad CSV, and those tildes over there is exactly this kind of thing I spoke about, that we have positional arguments, and we have to have some special value to just leave them as default. These in particular are the encoding and the types for the columns. But we're not interested in that at all. We need the one at the very end, which says that there is a header row. And this gives us a table matrix and then the names of the columns. I've used some special names prefixed with delta, and not to clash with anything else. You'll see why in a moment. So let's say that we wanted the last and first values. So we are sort of compressing our table to just have the columns that have the last name and the first name in that order. So we can look up last and first in the list of column names, and then we use that as the column indices in the table. Right? Then we can filter that, so we do a compressed but swapped, so we can have the Boolean mask after that. So here we want the last and the first name of those that live in Germany. So again, we index into the table, finding the right column that has the country, and then we see if the country is Germany. Okay, so it finds out that there are 2 people in this database that live in Germany. This is all traditional method of doing things, but let's see how it would look if we want to use a namespace. So here I put in a variant, this quad colon 2. This means I want an inverted table. This means that I want, instead of a matrix, a vector of vectors. And when we have character vectors, values, I want those to be given as vectors as well. There's another option with a 1 where we get it as a matrix, but let's not worry about that right here. Other than that, everything is the same. So now we're getting not a matrix, the first element of the result, but rather we get a vector of values, where the values are the entire contents of each column. And now we can use quad VSET. Right? We got delta cols is the names that are of the columns inside this table. So we make that into a matrix to tell quad VSET that this is a list of names. And then we give it the values for each one. So it's a list of values. So once that's been set, now we can make our query much neater than before. Notice there's no reference to the delta table anymore. Last is now a variable that contains all the last names, and first is a variable that contains all the first names. So we can construct a new mini table with 2 columns from those, and then we can filter it just by looking where country is Germany. This is a much neater syntax than what we had before, and that gives us our result. So you see that by importing to a namespace, in this case there's no mention of any namespace. That's because quad VSET was called monetically, so it just sets it in the current namespace. We don't need to do any references. So once we have everything in the namespace as variables, 1 variable per column, things become very nice. And we don't have to do this in 2 steps. We don't have to read in variables with the column names and the values for the columns. We can just insert. So we're using reduction here to just insert quad VSET appropriately between these. And we're not interested in the result now because it just has the side effect of making these variables in the current namespace. If we want, of course, we can get a reference. So here quad VSET takes a left argument, which is a new empty namespace, and that will then be the result of this reduction. So that goes into our database. So we get a database namespace, and then we can do queries inside the database namespace. So if you're importing multiple things, you might want to keep things like this. But again, not very complicated. We can even create a query function that does things for us. So I'll explain a bit how and what's happening here in this where function. So first, we are taking a namespace on the left. That's the alpha. Quad VGET -2. This gives us name value pairs. Then remember that the names are the column names of our table, and the values are vectors. So that means 1 element per row. Okay. The right argument of where is going to be a mask, a Boolean mask, for selecting things. And we need to compress every list of column values accordingly. We're making a query. We are winnowing down which rows are supposed to be represented. So we bind the Boolean vector, the omega, to compress and apply it to each of the second element at 2 of each of these. So again, quad VGET returns us name value pairs. We want to apply to each of the name value pairs. We want to apply not to the name, not interested in that. We're interested only in the values, which is the list of values 1 per row of our table. And for each one of those, we want to apply the compress, the omega compress. So where takes a Boolean vector right argument, and then it filters each column in turn. So this gives us now, again, name value pairs, but the values have now been shortened down. And we create a new namespace with quad VSET with a left argument, that's the open paren, close paren, to create a new namespace. And we set those new name with values inside this namespace. And then I put in the right tag there because quad VSET is shy. It just has the side effect of setting things, so it doesn't normally return a result. We can coerce it to return a result with the right tag. That's not strictly necessary. But that means when we're running where, we get a namespace out that we can capture and we can see. So then the call syntax becomes database, where the database country is Germany. Again, a very nice syntax, and we created a little DSL, a domain-specific language, that we can use for querying our database. Then we can create a function to view the tables, because now we're only talking about a theoretical table. It's a namespace that's containing variables that contain all the values for each row, but that you can't really view that in a nice way. So here's a view function added to our small language. Quad VGET2, this gives us a matrix of names followed by a vector of the values. So this is a vector of the first column, a vector of the second column, and so on. We take omega as left argument for VGET, so that means it takes the result from where? It takes a database. Then we insert a little function in between them, in between the names and the values. For the values, we do a mix. So this means we're getting now instead of a vector of vectors, we get a matrix, but it's in the wrong orientation. Every column is now a row, so we do a transpose on that. And the left argument, which was a matrix of names, we do a split on that. That gives us a vector of vectors, and that will form the header row. So we stack them on top of each other with concatenate first. And because we did a reduction, we have to disclose as well. Okay, the effect of this is we get a viewable table. So the order of the columns is not what we had before, because a namespace is inherently unordered. But I'll leave it as an exercise for whoever wants to implement the right order. The way you would do this is that you have special variables included in these namespaces that contains the names of the columns in the right order, and then you read those in and order things accordingly. So it's not very hard to do. But this is now a viewable table, but it came from a namespace, a way to view the namespace when the namespace lives up to certain requirements of being a table type namespace. So this is how it works. Traditionally, you would use execute to retrieve values, but we can use quad VGET instead. It's quite intuitive, and you can use it either a list of names or you can give it a matrix of names. Either way, you get the values out. And as we've seen, we can use -2 that gives us name value pairs, or 2 that gives us all the names as a matrix, and then the values. And of course, again, you can use any number you want, or any vector of numbers that is there to get things with specific classes, name classes. So often you want to set default values, and the way that we could do that with quad VGET is sort of an extension to the syntax. Instead of just having the names of the variables that we want, then you give name value pairs, just like with quad VSet. But instead of setting, it gets the value from the names. If any name is not available, then it will fall back to the value. So this is a built-in way to provide default values. That means you don't get a value error. If any name is missing, you'll just get the fallback value. You can also do this with a list of names as a matrix and then a list of values. And this also actually allows you to specify a single value as fallback value. So let's say that namemat is a matrix of many different names, and the values is just a scalar 0, for example. So any name that's missing will just get returned as the value 0, or whatever value you choose to use, of course. So let's go back to the function that we wrote before with the range, where we were merging in names from the default value. There's the literal namespace that's from 0 and step is 1. And then we merged in the parameter namespace, and everything gets merged into this namespace where we are now. Remember, I mentioned that if the parameter namespace contains additional names, then they will just pollute here. So this is not really the best way to do things. So consider this instead. Here on the right and the middle lines, we have, that is from the end of quad VGET, we have a namespace, and specified as name value pairs, right? This is not a namespace. It doesn't say from colon 0 and step colon 1. We could possibly make this extension in the future, that you could do that. But notice that the third row just says 2. So what we have here is really just a vector. This is the vector notation. And it has 3 elements. The first element is itself a 2-element vector from 0. The second element is also a 2-element vector, step 2. And the third element is just a bare name, character vector 2. So quad VGET, taking this vector, this list, as right argument, params as left argument. That means we're getting the values of from, step, and 2 from the parameter namespace. But if from is missing, we'll return 0. If step is missing, we'll return 1. If 2 is missing, we get a value error. So now it doesn't matter if the parameter namespace contains additional things that we don't need, because we are only getting from, step, and 2. And since we know that we're going to get a 3-element result, we can do the assignment then to from, step, and 2 in where we are right now. So it's a very nice way to get default values. Now if we inline that for a moment, then we can look at how do we deal with any errors. There could be the error of 2 being missing. That's a value error. But there could also be other other errors. If the numbers don't add up, so that the division gives a non-integer value, or if we have a higher starting point than the ending point, so that we try to do iota on a negative value, then we would get domain errors. And for a proper utility function, industrial strength, we don't want the function to stop inside. So we're going to add a trap. So we're trapping any error that happens in our retrieval and computation. And then we want to propagate this error up to our caller. And traditionally, you'd have to extract from quad_dmx, which is a namespace containing the error information, the exact pieces, and you have to create a proper argument for quad signal using this. It's tedious and error prone and repetitive. But here we can use these new system functions and extended system functions to do the exact same. So we have quad_dmx. We go into that with a dot. Quad_ns, create a new namespace, which extracts or copies the values en, em, and message. Those are the important parts that we want from quad_dmx, from the error information. Now we have a new namespace. We can use quad VGET with a right argument. I swap the arguments with the commute operator of -2. This gives us name value pairs. So effectively we get that the character vector en followed by the error number as one element. Next element, character vector em followed by the main message, and then a character vector message followed by the extended message that we want. And this is the proper argument for quad signal, just needs an enclosure. And then we can call quad signal. So this gives us a neater way to what I call re-signal. We're taking an error and we're bubbling it up to our caller without having to worry about exactly how to specify things for quad signal. Sometimes this is actually a problem, because if we trap every error and something goes wrong, we don't understand what it is that went wrong, then we've excluded ourselves from debugging. So let's give an optional debug left argument to range. So now we're using quad VGET. We're trying to get the value of debug. If it doesn't exist, then we'll use the value 0. Notice the enclosure here, because it's the single name value pair. So quad VGET debug 0 here. If there's no left argument to range, then we'll return 0. We do 0 drop 0. That's a 0. And that means we trap all errors. If you set debug to another value, so that would a 1 or a -1 or something like that, then we drop the 0 and there's nothing left. We do no trapping, and that means we'll stop an error. So this provides us a new way to deal with ambivalent functions. The traditional way is you have to check whether the name class of the left argument name is 0. Dyalog also provides a special I-beam to do it, but this is quite readable. It just get the value of debug, and if it doesn't exist, use a 0, and you could use any value, of course. In fact, we don't even need to do trap 0 and drop. We can be cleverer yet. So this is trap using the value of debug and defaulting to 0. So that means if there's no left argument to range, we do trap 0 because that's the default value for debug. That's what quad VGET gets. And if you want to trap only some errors, you can use the left argument to range to specify which errors you want. Very often, the only error I want to trap is a workspace full. That's one I can't deal with. It's not my algorithm that's wrong. It's just the computer can't keep up. So if we set the left argument of range to 1, debug to 1, that means trap only workspace fulls, and anything else, we stop the execution. But you could also be specific. You want to trap only specific errors and not other errors. So this is a very nice method to do a dynamic error trapping. Okay. In summary, we've seen the new array notation for matrices, or indeed higher rank arrays. We have for vectors. We have namespace notation. We have a notation for a new empty namespace, something that's very often used. Then we have the new ways of merging namespaces, where we can both take a reference as left argument in addition to the traditional character vector that's the name of the namespace we want to merge into. And we can use multiple namespaces to the right of quad-ns to have a sequence or a hierarchy of namespaces that get merged into the target namespace. We have the various ways of getting values. We can just plain get the values of some given names. We can have a list of names that changes nothing in the result. We can say we want all the variables, and or we can say we want specific names with fallback values, and we have both the vector and matrix, so name value pairs and single matrix of names and the list of values for getting names. And finally, we have this way of setting things without using execute. Again, we can use either name value pairs, or we can use a single matrix of names and then a list of values. And just remember that we have all these defaults. These are good ways of setting defaults. When we're using parameter namespaces, then the default of quad-ns is the left argument, and anything comes from the right overwrites the default. When we're using multiple, then whatever is further to the left is the default, whatever is to the right overwrites that. In quad VGET, the default we have inside the name value pairs is that value, and we can use a matrix with a list of values, and in there we have all the default values for all the names we have, and then we can go and do other things after that.